but Professor Joao, Irish SOUSA, is going to give the next talk, ML prediction of CH bond energies, calibration of DFT-based models with experimental data.
So thank you for the introduction, for your efforts to announce my name. I know it's difficult. And I'd like to thank the organizers and Professor Van Eyck for this opportunity to be here and for setting up this wonderful event. Today I'll talk about using small data sets of experimental data concerning bond dissociation energies to calibrate machine learning models trained with DFT calculations. This follows a project started some years ago to develop machine learning approaches for fast prediction of properties calculated by quantum methods. The main idea was to build large data sets of quantum chemistry calculations in a first computationally expensive step. But then when we have these data sets, we can use them to train machine learning models that can be used for fast predictions and that can be put into simple devices for fast predictions of these properties. This approach has been meanwhile explored by several groups for predicting several properties of molecules, of atoms, of bonds, and this is particularly useful when we don't have large data sets of experimental data, when we don't have access to experimental data, or as I will show you later, for knowledge transfer using small data sets of experimental data. So I will show you what we did with homolytic bond dissociation energy some years ago, and then how we tested now these models with experimental data and how we calibrated the models with experimental data. We started with a data set of almost 14,000 bond dissociation energies for compounds with these elements calculated by DFT at this level of theory. We explored neural networks and random forests and designed descriptors to encode atom types and the 2D environment of the bonds. These descriptors are essentially counting of atom types in spheres around the bond, and they are defined in terms of the element and or the element plus the number of neighbors. This is an example for descriptors of this bond. So you can see counting of atom types in specific spheres around this bond. Other types of descriptors were pairs of atoms of specific atom types within specific spheres and at specific interatomic distances. These descriptors were calculated before bond breaking and after bond breaking, so for the two fragments, and they were also calculated specifically for pi systems and aromatic systems. Okay, so with a training set of almost 13,000 bond dissociation energies over this range, we reduced the initial pool of almost 4,000 bond descriptors into 85 descriptors based on intercorrelations and random forests. The best machine learning was at the end an associative neural network, but random forests performed equally well. And this is the result for an independent test set of 887 bonds covering this range of energies, and we achieved typically a mean absolute error of about a bit more than 3 kilocalories, and this error is a deviation between the machine learning prediction and the DFT calculation for the bond energy. In the distribution of errors, you can see that most predictions are within 2.5 kilocalorie of deviations, and up to 90% are below 5 kilocalories. And here is a comparison with also fast predictions, although not so fast, using semi-empirical model calculation, PM6, and you can see that the machine learning predictions in black are better, although the PM6 calculations are also highly correlated. In this table, this is clearer. The neural network predictions are better than the PM6 calculations for almost all types of bonds, with the exception of hydrogen, nitrogen, and hydrogen, oxygen bonds because of non-covalent bonds, non-covalent hydrogen bonds that are possible with these atoms and that are not well predicted by the neural network because of the descriptors. I will show you an example later. And here is a test against bond dissociation energies calculated at a higher level of theory in order to check if the training set should be built with a higher level of energy. We can see that the same neural networks predicted these bond dissociation energies at a higher level with root mean square deviation of about 5 kilocalories, which is more or less the same as it predicted the first DFT calculations. And the deviation between the two DFT methods is much less. So it suggests that calculating data sets with a higher level of energy would not help much in this case. What are bad predictions? It is an example. This compound, we have two hydrogen-nitrogen bonds, which are topologically equivalent. So the neural networks predicted them to have the same bond energy, but in fact, they have different DFT calculated because of a 3D conformation, and that makes it possible hydrogen bonding, and because the descriptors that we're using do not take into account the 3D structure of the molecule to be faster, and could not take this into account. Okay, these models were implemented into a web service. You can try if you want. You can draw the structure and get the predictions from random forests or neural networks. You'll see the predicted bond dissociation energies. Here you can use it even in your mobile phone. Okay, now we focused on carbon-hydrogen bonds, particularly on bonds involving carbon, sp3 hybridized carbon. So a local model, the model that I've shown you before, that I had built before, was a global model, and so this is a local model specifically for these types of bond. This is a subset of the training set. The descriptors now can be much simplified because one of the fragments is a hydrogen, and it's always the same. So we basically can use atomic descriptors of the carbon atom. That's what we have used. And these were essentially counts of atom types specified by the element and number of hydrogen neighbors in the spheres around the carbon atom. And we explored these with random forests. Here we search for what is the impact of increasing the number of layers around the carbon atom, how it would impact the predictions, and for out-of-bag random forest predictions of the training set, you can see that increasing the number of descriptors with more and more spheres further than 5 did not improve the results. So we kept 5 layers of descriptors. Main outliers that emerged during this optimization were related to bonds connected to rings, particularly fused rings. And so we decided to add some more descriptors that encode, that specify the number of rings of specific sizes from 3, including the carbon atom. And this, in fact, improved the predictions. So you can see that the error in the training set was significantly reduced. So we have some more descriptors in the final model. And this is the prediction for the test set. So we are comparing still predictions from the machine learning method, the random forest model, with the DFT calculated bond energies. And you can see that the mean absolute error and all the other parameters were slightly improved comparing to the previous global model, and they are a bit less than 3 kilocalories. So now we have a data set, not very large, but a data set of experimental data, and we tested these models with experimental data. Every time I was showing these models, there was always a question, how does it predict experimental energies? Okay, here it is. The error is a bit higher, R squared a bit lower. However, R squared is still relatively high, and we suggested some systematic deviations because of the DFT theory that we were using. We could take 409 bonds from this database. These were the bonds used for testing. And so we set up a protocol for calibrating predictions from the neural networks trained with the DFT calculations to correct these predictions with the data from the small data set of experimental data. This is how it works. We have the additional database of experimental data. This is a small data set with experimental values. When the energy is predicted by the random forest, we get an uncorrected prediction, so the original prediction from the random forest, but the random forest also produces an output profile. This is the pattern of terminal nodes at each tree of the forest, of the ensemble of trees in the random forest. And on the basis of this output profile, we find the k nearest neighbors in the additional database, those with the most similar output profiles to the query bonds, and we correct this prediction with the mean deviation for these k nearest neighbors. So the mean error observed for these k nearest neighbors between the experimental value and the value predicted by the same random forest model. And with this correction, we get a calibrated prediction of the bond energy. And here are the results for a test set of 82 bonds. So the whole data set was split, and 327 bonds were in this additional database, 82 bonds in the test set. And in fact, the predictions could improve considerably, achieving a mean absolute error around 2 or less than 2 kilocalorie per mole. And the last result is a comparison with a literature approach, Alphabet, which is also available as a web service from another group that used graph neural networks trained with almost 300,000 bond dissociation energies calculated at this level of theory, and could achieve quite good predictions of bond dissociation energies. So we took a common test set of 145 bonds and put the others in the additional data set and make the corrected prediction, the calibrated predictions, and the results were these. So 2.22 kilocalories, which is slightly better than this one, but it's more or less at the same level. Okay, so in conclusion, the fast predictions of DFT-based bond dissociation energies could achieve mean absolute errors about kilocalorie per mole, comparing DFT calculations with machine learning predictions. And for experimental values, non-calibrated predictions were at this level. And by calibrating the data in the output, taking into account k-nearest neighbors in the output space of the random forest, we could improve the predictions until mean absolute errors about 2 kilocalories. Finally, I'd like to acknowledge the contribution of my co-workers. First, Joao for the first part of the work, who's now working in the US at Berkeley, and the group of Professor Qinyu Zhang at the University of Henan in China that worked in this last part with the calibration of the models and with the experimental data sets. Thank you.
So we have time for questions before we go.
Just a question about the calibration process. Is it a two-step procedure? Say, first I compute all the random forest for the prediction of all my test elements, and then I am able to compute nearest neighbors? Or do you iterate one by one? Then the first element, it has no neighbor.
We run this additional data set through the random forests and get a prediction for each bond, a prediction and an output profile. And we keep this in this additional memory, in this additional data set. And when you have a query of a new bond, we look into this pre-calculated data set for the k-nearest neighbors, and we see how were the predictions for these k-nearest neighbors, how far they were from the experimental values. And the average of this error is added to the uncorrected prediction of the query bonds.
Okay, thank you.
Thank you. One more over there.
Point I didn't really get it. Is it homolistic or heterolytic bond breaking and homolytic?
Homolytic bond dissociation.
Last question.
The two fragments are neutral species.
How about the extension to the heterolytic bond breaking? Because if you focus on the CH bond breaking in a heterolytic way, it may be related to the PK prediction. Of course, in that case, you need to mind about the solvation, because the heterolytic reaction should be very sensitive to the polar environment. So
what about calibration?
Extension to the heterolytic bond cleavage? In this case, I understand this is homolytic, right?
Yes.
But have you ever tried to extend? Okay, I need to finish.
I haven't tried to extend it to but yes, in principle, yeah, the DFT calculations with this, but yeah, we could try that. Yeah. But we have not calculated. And also in terms of in terms of experimental data, you would have for some types of bonds probably. Maybe not so.
Okay, let's move to the next speaker. And Joao, thank you very much.